Welcome back, everyone. This is Professor Rood, and I'm going to start Chapter 2 lecture on rocks and minerals. This is not the main focus of this course, but being a geology course, it needs to be discussed in some detail. The differences in the physical properties of rocks, minerals, soils determines how suitable they are for different purposes. For example, do they contain water? Do they contain valuable metals? Can they be used in construction and manufacturing? What about waste disposal and agriculture and other uses? Here we see the mineral wolfenite. That is an oxide of lead and molybdenum. Do you know what lead and molybdenum are used for? You should Google that and find out. Before we get into the details of minerals, we want to start with atoms, the smallest particle into which an element can be divided by still maintaining the chemical characteristics of that element. Remember, atoms are made up of a nucleus with surrounding electrons. The nucleus contains protons that have mass and a +1 charge, as well as neutrons that have mass but no charge. All of the mass, or the majority of the mass, is sitting in the nucleus of an atom. The number of protons tells us what element we have. For example, atomic number 1 is always hydrogen. Hydrogen always has 1 proton. If it has 2 protons, it's not hydrogen, it's helium. The number of electrons orbiting the nucleus determines the number of positively charged protons in a neutral atom. So the electrons are point particles with essentially no mass. They have a small amount of mass, but do not contribute to the overall mass of an atom in any significant manner. However, they definitely have charge, and it's a -1 charge. When we say we have a neutral atom, that means that the number of protons is equal to the number of electrons, because those are our charged particles. Here's a schematic drawing of the atom. We have a teeny tiny nucleus in the center, and then this, what we call probability cloud, electron cloud, where the electrons are moving around in 3-dimensional space. Protons are positive charged, neutrons neutral, electrons negatively charged. An element can't be broken down into anything else and maintain its properties. And for a particular atom, I already mentioned that an element for a particular atom has the same number of protons. I don't think I said that very well. So carbon, for instance, always has 6 protons. Hydrogen always have 1. So it is the atomic number, once again, that identifies what element you have. All nuclei, except for ordinary hydrogen, contain neutrons. An isotope of an atom is a variation in the element, and it varies in the number of neutrons. And if our number of neutrons is varying, then our mass number is also varying. Mass number is defined as the protons plus neutrons added together. Here's the periodic table of the elements. The top number is the atomic number, number of protons. Here's your chemical symbol. Here's your atomic weight, or atomic mass. We're going to be more interested with what I term mass number. So to determine your mass number for your element, you simply round your atomic weight using rounding properties. So carbon's mass number would be 12. Oxygen's would be 16. We don't need to worry about the actual weights for this class. Some atoms can become charged because they lose or gain electrons. Those are called ions. The term anion specifically means that the atom has gained electrons, and so it is negatively charged. So it has more electrons than protons. A cation, on the other hand, loses electrons and so is positively charged and has more protons than electrons. When we combine two or more chemical elements, we form compounds. Compounds are held together by bonds. Let's mention a couple here. The ionic bond is a bond that forms between ions. So there is a transfer of electrons with an ionic bond. Covalent bonds, on the other hand, share one or more electron pairs. Table salt is a substance that has a purely ionic bond. Here is the sodium atom. Here is the chlorine atom. Initially, there are 11 protons, which it has to have 11 if it's sodium. And we can see that the inner electron shell has 2 electrons, and the outer shell has 8. That is because the shell that was here, there was one more shell, had 1 electron in it, and it gave that electron to chlorine. So sodium lost an electron and therefore became a positive 1 ion. Originally, the chlorine only has 7 electrons in the outer shell. It wants that 1 extra electron and captures it. Now chlorine becomes a negative 1 ion, as shown here. There's a rule called the octet rule that says the most stable configuration for an atom is to have 8 electrons in the outer shell. And so this is what has occurred. Sodium loses its 1 electron, so the next shell in is full. Chlorine had 7, picks up that electron. It now has an outer shell that is full. And what holds it together, the sodium and the chlorine, is the positive and negative charges of those ions. That is the ionic bond. Let's talk about what defines a mineral. It must be naturally occurring, inorganic, must be a solid, it must have a definite chemical composition, it must be crystalline, that means it has atoms that are regular and repeating. We can identify our minerals in different ways, but by rite of passage, as a geologist, you need to identify them using what we call physical properties. Some physical properties include color, cleavage, hardness, and crystal form. So we'll look at a few of these. Crystalline means a regular repeating manner of the atoms. So here you can see in salt the sodium and the chlorine and the repeated nature. That means that it's crystalline. That's one of the criteria to be a mineral. Here we're looking at calcite. So we have carbon, oxygen, and calcium, and they're regular repeating. The internal arrangement of these atoms are oftentimes reflected in the external crystal form. That is how the mineral actually grows, its shape. This is an image of a scanning, tunneling microscope image of crystalline silicon. Note the hexagonal arrangement of the atoms. Quartz is hexagonal in nature when it exhibits crystal form. I think this is a good stopping point for our first video for chapter 2 on minerals. We'll look at some physical properties in video 2.